Hello everyone. So, this is lecture number 3 for the module 5, and in this lecture I am going to talk about the performance about the secondary storage, how we can improve the performance for the secondary storage, performance in terms of access time and the data transfer rate. So, in that connection we will discuss about the redundant array of independent disk or RAID levels. So, as we know that we have the memory hierarchy in the computer system beginning from cache memory to main memory to secondary storage. Initially there was no concept of the cache memory, then it introduced to reduce the access time for the processor, because processor speed is day by day increasing and the memory access time, main memory access time is not increasing, memory access time is not decreasing at that rate. So, the gap between the processor speed and the main memory access time is increasing, it is almost 10 times. So, for that the cache memory is introduced. Now, because the processor frequently access either like say cache memory or the main memory only, but sometime because the whole program cannot be put into the main memory, and that is the concept of the virtual memory, means your program size can be larger than the main memory. So, in that case your whole program is not in the main memory. So, during the execution of your program maybe sometime the secondary storage, because the rest of the program is there is in the main, not if it is not completely there in the main memory, then the some portion of the program is there in the secondary storage, and that is the concept of the virtual memory basically. So, when the data required or the portion of the program which is stored in the secondary storage required to be fetched from the secondary to the main memory, and then from main memory it will go to the cache and then finally processor will access. So, this delay between the transfer of secondary storage, because secondary storage are far slower than the compared to even your main memory access time and all. So, how we can reduce that delay, the transfer time from secondary storage to primary memory. So, that essentially we are looking for that some solutions we are looking. So, in this connection few arguments. So, in general we say that multiple components improve the performance. If I have more than one processor, let us say single processor have some capability, then I put multiple processors, then the processing speed will improve or much faster. Similarly, multiple disks should reduce the access time if they can be independently accessed and the different set of data is stored there. So, parallelly data can be accessed. For example, with multiple disks separate IO request can be handled in parallel. You have a multiple disk and IO request, multiple IO requests are coming, one disk is handling let us say at a time one IO request. So, that increase, even the secondary storage is slower, but still because parallelly multiple requests are handling. So, the overall request rate which is handled by the system will improve. That is a one way, that is how to the high IO request rate. Second possibility is a single IO request can be executed in parallel. So, some applications for that the access time is the critical. So, for these applications, or when you give the response and when you give the request and the response should come in a definite amount of time, that response can be in terms of transferring some amount of data. So, if this data that belongs to a single request is distributed across the multiple disks, then these multiple disks parallelly can, each disk is contributing some portion of the data, and ultimately it reduces the the time, the transfer time or data transfer time. So, a single request IO request can be executed in parallel if the requested data is distributed across the multiple disks. So, there are the two scenarios. One, we can improve the some applications which are there, they require the high IO request rate, that is a transaction oriented applications. Multiple users are simultaneously accessing. So, improving the performance of the system for these kind of application, and second is where the transfer time is critical or request response time is critical. You give the request and response should be come in some fixed amount of time, otherwise that system will fail. People will not use that kind of system. If I post a request and then I am getting response in very large time, let us say railway reservation system kind of thing. So, if I give a request for what trains are available between two stations, if it is taking too much time to give this information, I will not use that kind of system. So, there the response time is critical. So, for that if the request can be distributed across the multiple disks, then the time can be reduced. So, these are the two scenarios. So, to meet all these two basic requirements, researchers at the University of California, Berkeley, they proposed a multiple disk storage system that is called as a RAID, and it was developed in 1988. So, now what is RAID? RAID stands for the redundant array of independent disk. Means we have the multiple disk, and redundant word says that okay, you have some kind of duplicacy in the data maybe. So, one term that is a distribution of data, and one is a redundancy of the data, the two things which the RAID provides. There are 7 levels that is in common use, and some hybrid levels are also there, and these levels are not like that memory levels, cache to main memory to secondary storage to like that. There is no connectivity between the level 1 to level 2 to level 3, it is not a hierarchy as such, they are independent. So, the characteristics of the RAID are, it is a set of physical disk that is viewed as a single logical drive by the operating system. We have independent more than one disk are there, physically more than one disk, logically only one disk, and that logical perception is with operating system. So, operating system visualize okay, this is a one set of disk is there in a single chunk. Data is distributed across the physical drives, and each physical drive independently can be accessed. We can use redundant capacity to store the parity information. So, that it provides the reliability. If some disk fail, one disk fail or two disk fail, depends upon the level to level, which level we are using. It can support the fault, it can give the fault tolerance, and you can distribute the data. So, through the distribution the parallel access is possible. So, in this connection the first RAID level, that is called as a RAID 0, how the data mapping in the RAID 0 is there, that we can see in this picture. So, here you can see we have physical disk 0, disk 1, disk 2, disk 3, 4 disks are there, and data is distributed in the form of strip. Here I am saying strip 0, strip 1, strip 2, strip 3 and so on. So, data is distributed across the disk, and strip size is here critical. If you are making your strip size is very small, such that one request, IO request is distributed, the data related to one IO request is distributed on all 4 disks, then one request will come and that will be satisfied by all 4 disks. means the response time for that request will be reduced. Parallelly, you can say it is something like that, this job is divided into among the 4 people and the 4 people are working on that, definitely the total time required to finish the job will be less. If the strip size is large enough such that one strip contains the data that belongs to one IO request. So, similarly, strip 1 contains data for the satisfying the a single IO request. So, in that case 4 strips are there and they 4 different IO requests can be handled at a time. So, in case of the large strip size, the IO request rate, it will improve the IO request rate. So, here as such no redundancy of the data is not there. So, no redundancy. So, truly says it is also this RAID 0 is not considered as a RAID as such, because in the RAID R stands for the redundant and no redundancy here as such, only the data distribution is there across the disk, and this stripping is the round robin stripping. This is array management software here that gives the access. So, the access to individual disk is managed through this array management software and it gives a single logical view to the operating system. So, this operating system what it visualize, that is a single disk is there in which the data is stored from some 0 to some millions or trillions of words are there. So, this is the RAID 0. As I said that it is not even we cannot consider as a RAID because there is no redundancy as such. So, fault tolerance is not there. If one disk fail, in that case that corresponding data will be lost, we cannot recover. Now, let's look at RAID is it has a increased, the speed is increased. So, multiple data requests probably not on the same disk can be handled. Disk can be seek in parallel and a set of data is likely to be stripped across the multiple disks. So, that is how the RAID 0 data is mapped in the RAID 0. What is the drawback now? So, not a true RAID, okay, because no fault tolerance is there. Second is the failure of just one drive will result in all data in the array being lost. So, now how to provide the redundancy such that the fault tolerance can be provided. So, for this the RAID 1 is developed. In a RAID 1 you can see here there are 2 group of disk is there. This is a one group of disk and this is another group of disk. Data is again in the form of strips, it is distributed across the disk. So, it is a mirrored, 2 mirrors are there, same set of disk is this side and same set of disk is that side. So, for each data there are 2 copies, strip 0 2 copies are there, strip 1 2 copies are there. So, read and write operation. So, read can be done either of these. So, high availability of the data is there. In case of one disk fail, let us say this disk is fail, then data can be accessed from this disk and its copy can be created with the help of this disk. So, if your let us say your server is running and the one disk is fail, then you can remove that disk and you can replace that disk with the new working disk and the data will be automatically copied by the RAID system into the new disk and now your complete you will not lose any data in that case. So, it can tolerate one disk failure. So, let us summarize the RAID 1. The recovery is simple, data recovery as I said is simple, you can swap the faulty disk and the remirroring can be done. So, there is no downtime, on the fly you do not have to switch down your server and just remove the faulty disk, that can be indicated by some LED and put the new disk and do the remirroring, your data is ready. The drawback for this RAID 1 system is the disk overhead is too much, means multiple, you have just 2 copies. So, for let us say n disk of, you have a data for of n disk, so for that you require 2 n disk. So, the redundancy is 2n. Redundancy 2n, here n is the number of data disk. And another drawback is, for any write, let us say some information has to modify in the disk. So, let us say strip 0 has to be modified, and that modification has to be done at the 2 places, because there are 2 copies are there. So, write overhead is there. Come to the next RAID level, that is a RAID 2. So, in RAID 2, you can see in this diagram, you have here 1, 2, 3, 4, 4 data disks are there, and there are 3 redundant disks are there. Redundant disk, that not exactly the replica of the data is stored here, in this case you can see, that is an improvement over the RAID 1. Here the some parity information is stored of the data, so that if some disk is fail, then the data can be recovered with the help of this parity information. And storing parity information is advantageous because the amount of space which is required to recover the data is less. So, here for parity, Hamming code is used, and this is a bit level parity. So, you can say bit 0, bit 1, bit 2, bit 3 of these strips. So, the parity for this is F0b, F1b and F2b. So, a lot of redundancy is there in terms of, we can further improve this redundant information, because 3 disks. So, how many disks? Let us say I have total n disk data disk are there. For n data disk I require log of n redundant disk, log of n redundant disk. So, RAID 2, which is not in use in common, the reason is very simple, because the overhead is too much, it is a lot of wastage I can say. So, it use the parallel access technique, strip size is very small. RAID 2 and RAID 3 we will see that they use the small strip size. Error correcting code is calculated across the corresponding bits of on each disk or on each data disk, and multiple parity disks store the Hamming code error correction in corresponding position. So, error correction is Hamming code error correction. That Hamming code error correction is also used in the communication, data communication as well. So, now here question is, how many redundant disks are required? So, redundant disk for n data disk, it will be log of n. So, we have seen RAID 0 is not provide any redundancy. So, no fault tolerance is there, and for the large systems, large system in server class machine, the data availability or the fault tolerance is very important. We want a downtime is as 0. RAID 1 have exact replica of the data, so the storage wastage is there. There are certain advantages, that is why as a solution for a large computer system, RAID 1 is used. It is very common, because nowadays the cost of these storage, secondary storage or magnetic disk is very low. So, that is why too much of redundancy is not a problem, or exact replica is not a problem in terms of the cost of the system. But as an if you want to optimize the thing, then definitely the people use the different other RAID levels. So, RAID level is in common use, RAID 2 is not in use, because the advantage of the RAID, even the redundancy here also is even less compared to RAID 1, it is in RAID 2 it is less, but the advantage of the RAID 1 is the recovery is very straightforward. Remove the disk, put the new disk and remirroring. Here that recovery will take some time. That error correcting code will be calculated and then the faulty disk will be populated. If we replace the faulty disk with the new disk, then that disk will be population will take time. So, it is not immediately ready compared to the RAID one. So, that is the difference. So, now we are looking for the better solution in terms of the overhead should be less. So, here in a RAID 3 you can see here there are 4 data disk are there. Let me name these 4 disk, let us say is X0, X1, X2 and X3, and this is the redundant disk that contains the redundant disk, or it also called as a parity disk and named as a, let us say, X4. So, it bit interleaved parity is stored. So, the bit interleaved parity of B0, bit B0, B1, B2 and B3 is PB. So, only one redundant disk is required in this case. So, now how the data will recover in case of any disk failure? So, for that we will see, let us say in this case X2 is fail. So, first we will see how this for ith bit, how the parity will be stored in the X4 disk. So, X4 I stand for ith bit is equals to X3 I, and this is XOR operation, that is why it is a bit interleaved parity, then X2 I, X1 I, X0 I. So, the corresponding bit parity will be stored in the X4 at ith position. Now, let us say this X2 disk is fail. It is out of order. Now, how to recover the data which was stored in X2 disk? So, for recovering we will say add X4I, X2I on both sides of equation, both sides of equation 1. If you are adding both this on the both side of equation 1, then XOR operation. So, here I am not writing that step, X4I plus X4I and XOR operation same bit means it will be nullify. So, it will give me at left side X2I. Because if X4 is, let us say X4 is 1, X4I is 1. So, 1 XOR 1 is 0. If XOR is 0, then 0 XOR 0 is also 0. So, that is why it is a nullify. So, it will left side X2I will be left and right side, because what I am adding? I am adding X4I plus X2I, plus means it is XOR operation only. So, in this right side X2I and X2I will be nullify and you will get X3I So, what you will get? X3I, X4I, X1I plus X0I. So, now because X2 is failed, so you do not have any information related to X2. So, X2 you can calculate by adding the X3I, X4I, X1I, this is X1I and X0I, that all you have. X0 is okay, so 1, 2, 3, 4, so 3, this is x 0, yeah, this is x 0. So, x 0 you have, x 1 you have, x 2 you do not have, 3 and 4 you have. So, with the help of these 4 disks you can calculate the bits of x 2 disk. So, this is the way how you can recover the data which is lost. So, one disk failure it can handle. So, RAID 3 as far as the parity information storage wise, it is similar to RAID 2, only difference is only one disk is required, and the simple parity bit calculation is a simple. Now, this RAID 3 can achieve very high transfer rates. High transfer rate means single IO request is there, that if this request can be handled with the multiple disks, then the transfer rate will be high. So, how it can be achieved? RAID 3 use the strip size. Strip size is very small, maybe it's a 1 byte or 2 byte, is very small. So, with the help of small strip size, your single request is distributed across the multiple disks, and one request can be entertained by the more than one disk, and the parallelly it can be done, and the time will be reduced or transfer rate will be improved. Now, come to the RAID 4, the next level. So, in RAID 4, if you look at the difference, so here difference is a block wise parity is stored in compared to the bit wise parity. So, here block 0, and from RAID 4 to RAID 6 we will see the block size is, or the strip size, block is nothing but it is a strip only, the strip size is large. So, strip size large means it is good for the high IO request rate. Large strips good for the high IO request rate. One parity disk is there for, so if I have a total n data disk are there, then the total number of disks required to design this RAID 4 is n plus 1. Here n is the, so n plus 1 is the total disk. Out of this n is the data disk. So, one extra disk you require, one extra disk is there, that is a overhead you can say, or block level parity is used. Any drawback you are visualizing here? Okay, let us look at how the read write will be happen in this RAID 4. For read write block, let us say some request, modify request for the block 0 is there. What has to be done? Block 0 contents will be modified, simultaneously the parity information also has to be modified here. Simultaneously, let us say someone access the block 1, because it is good for the high IO request rate. So, multiple IO requests are coming, one for this, one for this, and one for this. So, in that case, for all these, let us say modifications are there, this parity block or this parity disk will be accessed. Maybe it is not necessarily that okay 0, 1, 2, 3 will be accessed, maybe 0 then 5 will be accessed from here, here from 11 access. Irrespective of whatever block is accessed from the independent disk, the parity disk is only one, and that will be always be accessed. So, this parity disk can be a bottleneck. Here a long queue can be there for writing the parity information corresponding to the blocks. So, that bottleneck is there. Now, how to overcome through this single place bottleneck for writing the parity information? So, that has been achieved in RAID 5. So, in RAID 5 this parity block is distributed, or this parity disk essentially is distributed across all the disk. So, here also the number of disk required is the same. If 4 data disks are there, then one parity will be required. So, 4 plus 1. So, n plus 1 be the number of total disk required to design a RAID 5 for n data disk. But the only difference is the parity block is distributed across the bit, across the disk. So, single point bottleneck is resolved here. So, parity strips are also allocated through the round robin fashion, and this RAID 5 is commonly used in the network servers. It is a very popular RAID 5. Most of the network server systems, the RAID 5 is implemented because it is better in terms of the redundancy, also is less. Single point bottleneck of parity, sorry, RAID 4 is also not there. Any drawback? The disk failure has a medium impact on the throughput, because it is difficult to rebuild in the event of a disk failure compared to the RAID 1. Suppose in this case, let us say this disk is failed. So, if this disk is failed, means what you lost? You lost the block 2, 6, block 13, block 17. So, block 2 can be recovered by this parity information, block 6 can be recovered by this parity information, and this parity is also parity from 8 to 11 is lost, but 8 to 11, 8, 9, 10, 11 their blocks are already there. So, that parity can be reconstructed after replacing this, and 13 and 17 also can be, 13 can be get from here and 17 can be get from here. But one disk failure it can sustain for one disk failure, but the rebuilding is comparatively to the RAID 1 is difficult, or difficult in the sense it takes some time, it is not readily available. So, in the RAID 6, so the difference between RAID 2 and RAID 6 is that compared to RAID 5 and RAID 6 is RAID 5 we calculate one parity information, RAID 6 we calculate two parity information and are distributed across the disks, all disks, not a single disk like in a RAID 4 have the parity information. That two parity information is distributed across, and these two parity blocks are stored in separate blocks on separate disk. So, it provides high data availability. In this case, it requires 3 disks to be fail to lose any data. Minimum 3 disks should fail. Up to the 2 disk fail, there is no loss of data, data can be recovered. So, for high availability where the data availability is a major concern, for these kind of system RAID 6 is better. Definitely due to the 2 write parity calculations, there is a significant write penalty is there, or write overhead is there. Any single modification requires 2 parity information has to be changed, because these 2 parity information are for the same data, and that provides the high availability. So, in this case you can see, if you fail 2 disk, you can see the failed 2 disk, any 2 disk randomly you can fail, and the data can be, you can see the data can be recovered. Block 1 can be recovered now with the help of either of this or this, and parity 12 to 15 is lost, and the 12 to 15 data can be recovered from here. So, in any case, any combination you can try, if the 2 disk fail, still these 2 disk data can be recovered and your system is with 0 loss of data, your system can work, all the data can be recovered. So, number of disk which is required, or the overhead disk, I say overhead disk is 2 here. So, if you have n data disk, then you require total number of disk is n plus 2. This is total disk. That is n plus 2. So, 2 disks are in overhead. So, the drawback, as I said, the controller overhead to compute parity is high, because 2 parity has to be calculated. So, that is the only drawback, otherwise availability wise it is good. So, these are the 7 levels 0 to 6. We just did the comparative analysis of all these 7 RAID levels. Some hybrid RAID levels are also popular and used in computer systems, network servers and all. One of the level that is called as a RAID 1 plus 0. So, what is RAID 1 plus 0? means it is a combination of RAID 1 and RAID 0. What is RAID 1? RAID 1 is a mirroring, RAID 0 is a stripping, round robin stripping of the data. So, RAID 1 plus 0, how it is constructed? RAID 1 plus 0. So, first mirroring. So, one side 2 disks are there, A1 A1, A3 A3. So, that is the mirroring, A5 A5. This is one mirror, and another mirror is A2 A2, A4 A4, A6 A6. So, this is RAID 1 and this is RAID 1. This also RAID 1. Now, to combine this is your RAID 0, and in total it becomes RAID 1 plus 0. So, first we are doing mirroring and then the stripping. So, it provides high level of I/O performance, data redundancy and the disk fault tolerance. How? Let us say it can support 2 disk failure. How? Let us say this disk fail from this side and this disk fail from this side, still data availability is there, you can recover the data, because your data is 1, 2, 3, 4, 5, 6, all blocks are there. So, the condition is what? It can sustain on 2 disk failure if these 2 disks are fail from either side of the disk system. One disk from this side and one disk from this side, any disk fail, you can take any combination, but one from each side, either this or this, the data availability is there. So, 2 disk failure it can tolerate. So, that gives better performance compared to your RAID 1 and RAID 0. Next is RAID 0 plus 1. 0 plus 1 is also, the construction is more or less similar in the sense here, because it is a reverse of RAID 1 plus 0. RAID 1 plus 0 is also called as a RAID 10, and this is RAID 0 plus 1. In 0 plus 1, first do the stripping and then do the mirroring. So, for stripping, again minimum number of disks required here is 4, 2 one side and 2 other side, and then do the stripping, that anyway common in all RAID levels. Stripping is common in all RAID, whatever RAID level is there, data is stripped across the disk for parallel accessing. Now, first construct the RAID 1. RAID 1 means simple stripping, sorry, RAID 0, 0 plus 1, so RAID 0 do. So, A1, A2, A3, A4, A5, A6 and so on. And now, here also you do the same stripping, A1, A2, A3, A4, A5, A6. So, this is your RAID 0, this also RAID 0, and now because it is mirrored, so now this becomes RAID 1, and finally it looks like RAID 1 0 plus 1. So, how it is different from RAID 1 plus 0? What is the difference in terms of fault tolerance? So, here I mentioned it is slightly less fault tolerance than RAID 1 plus 0. Why? Can it tolerate the 2 disk failure at a time? It can tolerate 2 disk failure, but these 2 disks, let us say this is a 1 disk fail and this is another disk fail. In this case, we lose the data. The block A1, A3, A5 are lost. So, 2 disk failure if from either side one from one side, another from one side, the data cannot be recovered. If these two disks failure at one side only, let us say this one and this is okay. So, in that case the data can be recovered. So, that is the difference between RAID 1 and RAID 1 plus 0 and RAID 0 plus 1. So, RAID 1 plus 0 have the better fault tolerance or compared to the RAID 0 plus 1, because the chances of failing from one side, two disk failure, both the disks from one side are less compared to one disk can fail from one array and another disk can fail from another array, that chances are more usually. So, this RAID 0 plus 1 can survive, or the data the tolerance is only in the case of when the data is or disk is fail from one array. In the both the array disk is fail, if the same disk are both the array A1, A3, A5 in this case and A1, A3, A5 from this if fail, then data cannot be recovered. So, in that sense 1 plus 0 is better than 0 plus 1 in terms of the fault tolerance. Now, look at some review questions related to this lecture. First question is, in the context of RAID, what is the difference between parallel access and independent access? Second question is, what is the role of strip size in RAID 0 to achieve high IO request rate and high data transfer capacity? So, you have to tell the strip size should be small or should be large for high IO request rate and high data transfer capacity. To improve the high data transfer capacity, what should be the strip size? So, it is related in terms of whether strip size is small and large. So, that you can answer from this lecture. So, finally, look at what we discussed in this lecture. We talked about the reliability and performance improvement for the secondary storage. Secondary storage is a slower storage access time wise. So, how we can improve, and for that improvement we talked about the different RAID levels or redundant array of independent disk. So, thank you very much. Have a nice day.